I'm John Appleyard from Polyhedron Solutions, and I'm going to be giving a short technical overview of plusFORT. plusFORT is a Fortran programmer's toolkit for programmers who are refactoring or maintaining Fortran code bases. For plusFORT is delivered as a GUI, and you can do everything within the GUI. You can set up your configuration files. You can run the plusFORT components, and you can inspect the output all within the GUI. Alternatively, you can run it from a command line, and that's often a more appropriate option if you're doing batch processing or overnight, or making it part of a regular procedure. However, in this talk, we're going to be looking more at what plusFORT can do rather than how exactly you go about doing it. And we're going to start with the refactoring options. So SPAG, the spaghetti unscrambler, takes a Fortran source code input and produces a refactored source code output. And as you'd expect, it does the standard prettification type operations, standardizing the case of different tokens, standardizing spacing, converting hollow strings to character strings, standardizing relational operators, and so on. SPAG gets its name from its ability to restructure antique Fortran code, the sort of legacy stuff with lots of go-tos that used to characterize Fortran back in the last century. Here's an example of the sort of thing I'm talking about. This is a piece of really dense spaghetti involving lots of go-tos and arithmetic ifs. And here's what SPAG can do to it. It removes all the go-tos and makes it into something that you have a hope of understanding and following what's going on. That example involved introducing lots of block if constructs to replace the go-tos, but sometimes the go-tos would point backwards, and in that sort of case you've got to introduce do loops to replace the go-tos, and SPAG does that as well, and these are two examples. Now things can get even more complicated, and in some cases the go-tos can be decoded by introducing internal subroutines, and that's what SPAG has done here. It's introduced two internal subroutines and managed to replace this spaghetti logic over here. In fact, no matter how dense the spaghetti, SPAG can always find a way to get rid of all the go-tos. Another weakness of old style antique Fortran was the lack of strong typing. For example, in this case, you can see that although one variable A has been declared, there are two variables B and C which have not been declared. In a case like that, SPAG can insert the missing declarations and in addition insert implicit none so that the same sort of problem won't happen again. In fact, SPAG can go further than that and completely rewrite your declaration sections from scratch, adding intent and updating legacy types. So here's an example of the sort of thing we might have, which includes implicit none and all the variables are declared. However, if we ask SPAG to rewrite the declarations of that code, it will come up with this, and you can see that all the declarations have been rewritten. The dummy argument declarations are organized here, and we have, for each one, we have the intent specified. SPAG analyzes how the dummy arguments are actually used and deduces what the intent is. It's also replaced the types using the standard types, which are defined in Fortran 2003 standard module ISO Fortran.env, which so double precision is now, variables are now declared using this style of declaration, which is now perfectly standard. SPAG can also replace the old common and include statements in Fortran with modules. So if you have an include file, shall we say abc.inc, which includes declarations, then SPAG will replace it with a use statement to bring in a new module called iabc.f90, which it creates. So in effect, replacing the include file with a module. SPAG can also convert isolated common block declarations with modules, but there are some restrictions on that. Finally, SPAG can create modules with interface blocks to allow the compiler to check that dummy and actual arguments match. And there's much more that SPAG can do. For example, if you've got code blocks which are unused, then SPAG can optionally remove them. Likewise, variables which may just be clutter, you can have SPAG remove them. And there's other things that you can do, like variable renaming. You can have SPAG rename variables in a systematic way across your entire program. You can introduce directives into the source code to direct how SPAG should restructure the code. There are things like complexity metrics and a lot of other stuff that is in more detail than we can go into here. The next thing I want to talk about is global static analysis, which in plusFORT works a bit like compile and link phases of a standard build. So the compile stage is represented by SPAG, and SPAG analyzes individual subprograms and produces symbol files. The link phase, if you like, is done by a program called gxchuck, which reads all the simple files and produces a report. So if you change one piece of code, one subroutine, then you don't have to reanalyze the entire source code. You can just analyze the one that's changed and then rerun the global analysis. The outputs from global static analysis can be a simple text file, or more usefully perhaps an HTML file with hyperlinks connecting all the variables and reports. The output includes aggregated usage for include files as well as for individual variables and modules and so on. There's also a call tree and some analysis reports which are helpful when modularizing your program. So these are some screenshots from the HTML report, but I think if you're interested, what you should do is find the example you can interact with on the fortran.uk website. In addition to those reports, gxchuck can insert documentation back into your original source code. So in this case here, we've got a subroutine, and we've inserted a summary of the external interfaces to that subroutine actually inside the source code. If you look at a traditional Fortran program, then it comprises a lot of subroutines and a few functions perhaps, and a lot of data areas like common blocks. There are two reports produced by Global Static Analysis which can help you to sort out that structure. The first is an internalization report. Now this looks at subprograms and works out whether their scope could be reduced. So for example, one subprogram which currently has a global scope is only actually used within another subprogram, so it could be internal. So to what extent can we internalize subprograms is what the internalization report will tell us. The second report is a cluster analysis matrix, which attempts to find modules, to identify modules which could group together different subprograms and data areas in a way which is consistent. So for example, if you've got a group of subprograms and data areas which are related to your treatment of a grid, then you might have a grid module which groups all those subprograms and data areas together. And the cluster analysis matrix attempts to find ways in which you can divide your program up into modules. So given this as our starting point, the objective is to convert it to something like this, where the original structure with lots of isolated subroutines and data areas is replaced by two modules containing some subroutines from the left and some data areas from the right, and one subroutine which contains some internal subprograms and some data areas. Now, of course, gexcheck doesn't actually do the mechanical work of assembling these modules and subroutines itself, but it does give you an idea of exactly how to do it. The final part of this talk is about instrumentation, the ways that SPAG has to allow you to create a test program with special code implanted inside, which enables you to determine certain things about your program. One thing, for example, is timers. You can have SPAG insert code to monitor the time usage in each subprogram. So having planted the timers, you recompile and relink your program as before, and SPAG produces an output file at the end of the run which details exactly how much time has been used in different parts of the program. And this is an example of a very brief example of such a report. So, for example, in this case, a lot of time is spent in this routine try solve, but the stars represent work actually within the routine. Minuses represent work done not within the routine, but in routines called by it. The next thing we're going to look at is dynamic analysis. Dynamic analysis is monitoring a code for illegal usages, for example, if a variable is used before it has been set. Here's an example of a very simple piece of code that reads in some values from an outside source and then runs through them all, checking against a value that's passed in through the argument. Now then, if this is the data that's being read in, then you can see that the 21st value there is not specified. So you would get a use before set error when we get to the 21st iteration of this loop, but not before then. SPAG can detect errors like that by instrumenting the code. First of all, it inserts calls which undefine certain variables. Well, it does that by inserting a special undefined value in those variables. And then whenever a variable is used, it checks it to see whether it's still undefined. And if it is still undefined, then it can report an error which you can retrieve at the end of the run. So this is an example of the log file that comes out with a full trace back of where the problem occurred. Many people think that static analysis is a good way of detecting the use before set error, but that's not really true, at least not in general. Static analysis, for example, doesn't check individual array elements, and it doesn't handle dependence on external data, and it's really confused quite easily by dummy arguments and equivalents. And all of those things are areas where dynamic analysis, as described in the previous slides there, will detect the error. On the other hand, static analysis does check code whether or not it executes, whereas dynamic analysis can only look at code which actually executes. So you can see that these two approaches are complementary. If you use them both, then you're likely to have a better result than just relying on static analysis. The final area where SPAG can instrument code is for test coverage analysis. So when you're validating a program, you perhaps run a series of tests, and a reasonable goal for that is to ensure that every line of code is executed at some point in that series of tests. plusFORT can create an instrumented version of your program to monitor your progress against that goal. In essence, it inserts calls to a probe routine at various points in your code, and there's an additional library which has to be linked in. The source code is provided with plusFORT. And there's a post processor which, as you proceed through your series of tests, you can use to monitor progress against that goal of ensuring that every line of code is executed. This is a sample output from the POST processor, and it shows for each subroutine, AACalc, ACalc, ACPalm, etc., how many untested code blocks there are within that subroutine. And if there are some, it also lists the line numbers of the start of the code blocks which are untested. It also, as an extra output, shows the most executed lines in your entire program, which can be useful. The coverage analysis post-processor can also optionally annotate the source code with the execution count of each line, as shown here. Well, that's the end of the discussion of the SPAG and GX chook, but plusFORT does contain other tools like, for example, Hyperquick, which works on languages other than Fortran, works on C and Python and so on. And it's a hyperlink keywording context report. So, for example, we have a source file here, a C source file, and all the variables in there are hyperlinked. And if you click one of the links, you get a report of all the other places where that variable occurs. And you can switch quickly between the different reports, and you can save reports in the top here as well. So there's a lot more to plusFORT than I've mentioned, but enough is enough. We're on over 15 minutes already, so bye-bye for now.